So with that, we're going to move into our first keynote, or our second keynote, our first speak of the day. John Scott, who is the Associate Director of the Emerging Contaminant Center at the Illinois Sustainable Technology Center. His work focuses on the occurrence, fate, and impact of contaminants in environmental systems, with particular interest in emerging contaminants like PFAS and microplastics. At ISTC, he supports interdisciplinary research efforts aimed at understanding contaminant behavior in the environment and developing strategies for pollution prevention and sustainable solutions. John has contributed to numerous collaborative research projects and publications addressing environmental contamination and emerging environmental challenges. And today he's going to talk about emerging contaminants, what we've learned, where we are now, and where we're going.
Good morning. So before I start, I just want to ask a couple questions. How many of you are working in the area of PFAS? Raise your hand. Wow. How about plastic pollution? Okay. What about something else? What is that something else?
General contaminants in groundwater.
Okay. Somebody else? Sarah.
Legionella in groundwater.
There you go. Anybody else want to throw something else out? Antibiotics, great. So the point is that it's a lot broader than just PFAS and plastics. And that's really what makes this field so enjoyable and exciting. It's just the diversity of it. So I'm just also out of curiosity, I'm kind of doing an experiment here. How many of you are in the physical sciences? Chemistry, biology, engineering? How many in the social sciences? Oh, we're getting better. Okay, we're starting to see more of you, but we need more of you. It's a very important part of the puzzle. So I'm just, and the last thing is, how many of you are working on issues that extend beyond a certain region? Maybe they have an international impact. I should see all of you, because emerging contaminants isn't just a domestic issue, it's a global one. So that's exactly what, these are some of the things I want to explore today. There was a time when we didn't know. There was a time when the pesticide DDT was considered a breakthrough, a chemical that could save crops, control disease, and improve lives. It was used widely, confidently, and with the best of intentions. And at that time, the environmental concentrations we worried about then, the parts per billion, the parts per trillion, we couldn't even measure them then. The same was true for polychlorinated biphenyls, or PCBs. They were incredibly useful, stable, non-flammable, ideal for industrial applications. And for years, they were used everywhere, but largely invisible to us. It wasn't until analytical capabilities improved, until we started looking more carefully, that we began to realize that something just wasn't right. And today, we're having that conversation again with PFAS, with plastic. We can now detect these things at incredibly low levels across water, soil, air, and even in ourselves. We can detect more contaminants than ever before, but it doesn't mean that we're seeing the whole picture. And that raises a difficult question. Are there contaminants out in the environment that we haven't even discovered yet? So to explore that today, I want to frame my talk around several questions. And the first is, what have we learned? We've been here before with DDT, with PCBs. We've seen how these chemicals are introduced, how they spread, and how we eventually recognize their impacts. So this is really about understanding that pattern. Second, where are we now? Today's challenges, like PFAS and plastics, they fit in that same pattern, but under very different conditions. We can measure more, we can detect earlier, and we are seeing these compounds in ways that we've never seen before. So this is about understanding what's changed. And finally, what are we missing? Because even with all these advances, we're still limited by what we look for, and what we're able to measure. So this is really about recognizing what we may not be seeing yet. So let's start with what we learned. DDT is a good place to start. It was first developed in the 1930s. At the time, it was seen as a breakthrough, chemical that can control pests, improve agricultural productivity, and even combat disease. It solved real problems. In fact, the discovery of DDT, it was awarded the Nobel Prize. It tells you how significant that was at the time. This just wasn't fringe idea, it was leading edge science. And because of that, it was used widely, not cautiously, but confidently, and again, with the best of intentions. But at that time, we didn't understand how it behaved in the environment. And importantly, we didn't understand how it moved, how it accumulated, and how long it would persist. And importantly, we didn't have the tools to measure it. So it took years, really decades, before the environmental impacts became clear. Bioaccumulation, ecological damage, effects that we didn't anticipate. And by the time we understood the problem, the contamination was already widespread. DDT wasn't the only example. The same pattern played out again with PCBs. PCBs were introduced around the same time in the 1930s, but instead of agriculture, they were used by industry. Incredibly useful, super stable, non-flammable, and ideal for electrical equipment, transformers, a wide range of industrial applications. And for decades, they were used everywhere, in infrastructure, in buildings, in systems that we relied on every day. And just like DDT, they were used with confidence. Because at that time, stability was seen as an advantage. It was the very property that made them useful, is also what made them so difficult to deal with. Because that same stability meant that they wouldn't break down in the environment. They persisted, they accumulated, and over time they spread. And again, we didn't fully recognize the problem until much later, years, decades, after they had already become widespread. Today, we're having that same conversation, but this time it's PFAS, per and polyfluoroalkylated substances, a class of chemicals used in a wide range of applications, firefighting foams, industry processes, and consumer products. And like DDT and PCBs, they were designed to solve real problems. They're useful, extremely effective, and in many cases, we've already been using them for decades. In fact, many of these compounds were first developed in the 1940s and the 1950s. And part of the reason that we're seeing them so widely today is they don't come from a single source. They come from many different sources, many different pathways, entering the environment in different ways. But once they release their move, through water, through groundwater, across long distances, and which is why we're finding them not just near where they're being used, but we're finding them far beyond. In fact, one of the moments that really brought the attention to this was the compounds were detected in polar bears. Everybody loves polar bears. In remote Arctic environments from the obvious sources, which raised a very simple question: how did they get there? The answer is they moved through the environment, air, water, across long distances. And then it became clear this wasn't a localized problem, it was a global one. So we're starting to see them nearly everywhere in the environment: water, soil, air, and even ourselves. But there is something different this time. We can detect these things at incredibly low levels, parts per billion, parts per trillion, in some cases even lower, which means we're seeing the problem much earlier than we did in the past. We actually might be really not seeing something new, but just something sooner. And that raises an important question. What does it mean to detect something in the environment before we fully understand its impact? It's not just PFAS. We're seeing a similar pattern in plastics. They're part of our everyday lives. They're used everywhere, in packaging materials, products, the materials that we rely on every day. And that's also because that's why they're so widespread in the environment. But plastics are important, and they're different in one important way. At first, we can see them with our naked eye. We can see them in our lakes. We can see them in our waters. We can see them on the shorelines. But they don't stay that way. They break down into smaller and smaller pieces, from the macroplastic to the microplastic to the nanoplastic. And like PFAS, they persist. They just don't go away. And at some point, when they get down to those small sizes, they could be considered similar to PFAS. We can detect them, but we're still trying to understand what that means. With PFAS, we need instruments to see the problems, but plastics, at first we don't, but later we do. So the problems that we can see sometimes also can turn into ones that we can't see later. So we've seen this with DDT, we've seen this with PCBs, we've seen this with PFAS, we've even seen it with plastics. These aren't isolated examples. This is a pattern. We introduce a chemical because they solve real problems. Then we use them widely, but we don't fully understand how they behave in the environment. And only later do we begin to realize the consequences, only after they become widespread. We don't discover these problems when they begin. We discover them once they're everywhere. And that raises an important question then. How do we respond? If this is the pattern, how did we respond? Because discovery isn't the end of the story. It's the beginning, and it's where the real work begins. Let's go back to DDT. Over time, the environmental impacts became clear, particularly on wildlife. One of the best well-known examples was eggshell thinning in birds. Populations declined, ecosystems were affected, but then response was taken. Action was taken. Regulations began to emerge in the 1970s and when the science became clear. Use was restricted, and it was eventually phased out. And importantly, we saw bird populations recover. We saw ecosystems begin to recover, and species like the bald eagle became a symbol of that recovery. It wasn't immediate, it wasn't easy, and it wasn't perfect, but it worked. And when we act on good science, we can make a difference. And we've seen similar patterns with other contaminants like PCBs. PCBs were also regulated and again banned in the 1970s. But unlike DDT, the story is a bit different here. PCBs were much more stable. They persist in the environment, in our sediments, in our water, in the living organisms, which means they just won't go away. So instead of a more rapid recovery, what we're seeing is something a little slower, something that plays out over decades. And this is where monitoring becomes critical. One of the clearest examples of this comes from long-term monitoring in the Great Lakes. This data here comes from the US EPA's Great Lakes Fish Monitoring Program. This kind of long-term data is incredibly rare, but yet so valuable. It's important to recognize something here. The regulations came around the 1970s. Fortunately, this data set starts much later in the 1990s. So what you're looking at here is not the beginning of the response. It's the long-term outcome of an earlier action. These data track the PCB concentrations in fish over time, and you can see at the beginning of this record, concentrations are relatively still high. But over time, they begin to decline. PCB levels are declining, not quickly, but consistently. And it's what's important here is the time scale. This isn't change over a few years. This is change over decades. Decades of regulation, decades of monitoring, and decades of continued effort. And even today, these compounds are still detectable, still part of our systems, still part of the environment, which tells us something important. These contaminants, when they enter the environment, they just don't disappear. This isn't a quick fix. This is decades of progress. So while regulation works, it takes time. And without programs like this and the continued measurement, we wouldn't be able to see that progress. And without the visibility, we wouldn't know if what we're doing is actually working. So while regulation can work, it takes time, and it depends on long-term effort, long-term monitoring, and long-term commitment, which brings us to today. Where are we now? We're no longer going to be looking at problems that developed decades ago. We are in the middle of them with contaminants like PFAS and plastics. We're not observing the outcome, we're observing the process in real time, which means we have the opportunity to understand the problems earlier and potentially respond differently. So let's take a closer look at where we're at now. We can measure more than we can interpret. Our ability to detect contamination has improved dramatically. We can measure things at incredibly low concentrations across different environments, different systems, across a wide range of compounds. In some ways, detection is no longer the limitation, but understanding hasn't kept pace. We don't always know what these concentrations mean, how they translate to risk, or how they interact with each other. Detection tells us what's there, but it doesn't always tell us what it means. With DDT and PCBs, we discovered the problem late, after impacts had occurred. Today, we're often detecting things much earlier. But that doesn't mean we fully understand them. In some ways, we've shifted the problem. from not seeing to not fully understanding. And that creates a very different challenge. So what's so different about PFAS? First, they're incredibly persistent for organic compounds. Some of the most persistent organic compounds that we've dealt with before. They don't break down easy, which means once they get the environment, they're going to be around forever, for a very long time at least. Second, they're extremely mobile. They move through water systems, through soils, and across large distances, which means contamination doesn't stay in one place. It spreads. And third, extremely diverse. Unlike DDT or PCBs, we're not dealing with one compound or 100 compounds. We're dealing with thousands of compounds, many of them which we don't even understand at all. And when you combine these three things, this persistence, mobility, and diversity, it's a problem that's much harder to track, much harder to contain, and much harder to fully understand. And that's why, even though we can measure more than ever before, interpretation becomes the challenge. So how do we deal with something like this? And it's not just PFAS. We're seeing it when we look more broadly, we see this issue more widespread. With plastics, we're not dealing with a single material. We're dealing with a wide range of polymer types, copolymers, and chemical additives. Many of this stuff isn't even fully characterized. And as we've already seen, these materials can start off as something we can see and eventually become ones that we can't. And that complexity increases, and so does the challenge. We're not just asking, where are they, but what are they, how do they behave, what do they do? In many cases, we even know less about their potential impacts or their human health on ecosystems. This isn't just a continuation of the same problem. Each time it becomes broader, it becomes more complex and more or less understood. And in some ways, these are some of the most complex environmental pollution problems we've ever faced. So as these problems become more complex, the way we respond needs to become more complex as well. If we look back at DDT and PCBs, we eventually had a clear understanding of the problem that led to strong regulatory action. And over time, we saw measurable improvements. But today it's much more complicated. For PFAS, the science is still evolving. Regulation exists, but it's still developing. And in some cases, we're making decisions before we fully understand the science. We can detect contaminants at incredibly low levels, but just because we can measure something down to a certain level doesn't mean that we should regulate down to that level. Measurements tell us what's there, but it doesn't tell us what to do. It's part of the decision-making process, but not the whole process. And that brings up another difficult question. How do we regulate something before we fully understand it? Lots of questions here. So PFAS and plastics get a lot of attention, and good for reason, but they're not the whole story. And there's a risk of focusing too narrowly on the contaminants that we know the most about. Because our attention concentrates in one area, it can shift away from others. Not because they're less important, but because they're less visible. And if you think back to the examples that we talked about, legacy contaminants, those weren't obvious problems at that time either. They became problems once we started looking for them. So that raises the other question, what are we missing? Because our attention tends to follow what we can measure and what we're actively looking for. But that also means that there's things out there that we're not seeing yet. Not because they aren't there, but because we haven't identified them yet. Emerging contaminants don't wait for our attention. And that's why it's critical to think beyond these contaminants that we're currently focused on. These contaminants don't all come from the same place. They come from very different parts of our systems. Some contaminants from urban systems like tire wear particles and 6-PPD quinone generated simply by everyday transportation. Others come from consumer products, materials we use every day, things like siloxanes. Some come from agriculture, modern pesticides like neonicotinoids, dicamba, glyphosate, compounds designed to improve crop productivity, but also are entered directly into our environment. Others come from wastewater, pharmaceuticals that pass through treatment processes and continue on through natural systems. These are all very different sources, all very different chemicals, but they share something important. In many cases, we are still at the early stages of understanding them. We don't fully understand how they behave, how they move, or how they interact with each other. And in many cases, we're still learning on what their impacts may be. These may be today's emerging contaminants, they may be tomorrow's. But what's important to recognize, it's not fixed. It's constantly evolving. The pattern doesn't stop. New contaminants are always going to be emerging, not at once, not in a single place, but continuously, often in small ways, incremental, new compounds, new materials, new formulations. As industries evolve, as products change, as technologies advance, the chemistry changes with them. And often we don't recognize these changes as a problem until much later, just like what we saw before. And by that point, the compounds are already in our system. They're already distributed, already interacting, already part of the environment. And each time the system becomes more complex, more difficult to track, more difficult to understand, more difficult to manage. So we're not just solving old problems, we're operating in a system that's new ones are constantly emerging. So the question is not just how do we respond, but can we get ahead of it? What we have seen again and again is that we tend to react after the contamination has occurred. With DDT and PCBs, we didn't recognize the problem until it was widespread, until it was already in the environment, already in the ecosystems, affecting systems that we already care about. But at that point, our options were much limited, more expensive, more complex, much slower. But getting ahead of the problem is a different approach. It means shifting from reaction to prevention. It means identifying risks earlier before contaminants become widespread. It means thinking about how chemicals behave before they're used at scale, and ideally avoiding the problems altogether. Because the most effective way to deal with contamination is to prevent it from happening in the first place. It is the pollution prevention way. And it's not always easy. It's not always possible, but it's something we should be thinking about. So how do we actually do that? There's not going to be a single solution, and we can think about this in many parts. One part that I think about a lot is measurement. This includes both early detection and long-term monitoring. Identifying contaminants early and then tracking how they change over time. Seeing just not what's there, but how it's evolving. Second is design. Thinking about persistent mobility, toxicity before these chemicals are used at scale. Trying to avoid the problem instead of solving it later. And third, communication. Because none of this science works unless it's shared, understood, and applied. So getting ahead of the problem isn't just one thing, it's actually a system. Measurement, design, and communication all could be working together to help solve these problems. So let's start with measurement. One of the most important tools we have is early detection. Identifying contaminants before they're widespread, before they move to the system, before exposure becomes widespread, and before trying to clean them up. This is where analytical chemistry can play a crucial role. Because we have the ability to detect things so low levels. So the question becomes, how do we leverage these capabilities? How do we use this ability to detect things earlier and not just observe problems, but anticipate them? How do we move from measuring what's already there to identifying what might become a problem? Because detection changes something fundamental. It shifts when we see the problem. It shifts when we recognize it, and potentially it shifts when we can act. With DDTs and PCBs, we didn't have that opportunity. We saw the problem after it was widespread, but today we're seeing it much earlier. Earlier doesn't mean easier, because now we're detecting things before we fully understand them. Detection tells us what's there, but it doesn't always tell us what it means. And that puts us in a different position, not as scientists, but as decision makers. Because now we have to decide what to do with that information, even if it's still incomplete. So leveraging these capabilities just isn't a technical challenge. It's a scientific and a societal one, which brings us to the next question. What are we actually measuring? If we detect something, it's often thought of just a single concentration. But in reality, it's much more complex than that. In some cases, we're measuring compounds we already know, substances we identified, studied, and can interpret with some confidence. But increasingly, we're detecting things that we don't understand. Unknown compounds, compounds we didn't expect, or compounds we just haven't even identified yet. And then there's transformation products, compounds that form in the environment. Chemicals break down and react with other substances, which means that what we're detecting was not even what was originally released. And in many cases, most cases, it's not even a single compound at all. We're dealing with mixtures, combinations, interacting in ways that we don't even fully understand. So when we're measuring something, we're not just measuring a number, we're measuring a system. And that's why detection alone doesn't give us the full picture. It tells us what's there, but it doesn't tell us what it means. And there's a fundamental, and it brings us back to the fundamental challenge, not just detecting contaminants, but understanding them. So if we're actually measuring it, so if what we're measuring is this complex, how do we actually make sense of it? And this is where monitoring becomes essential. Not just measuring once, but measuring over time, repeatedly in different places under different conditions, building a record of how the system behaves. Because a single measurement tells you what's there at that moment, but it doesn't tell you where it's going, how it's changing, and what it might become. Like what we saw in the Great Lakes. This wasn't a one-time observation. It was decades of data collected, analyzed, interpreted over time. Slowly changing what would be impossible, or that's showing that change would be possible to see in any other way. Monitoring allows us to move from isolated observations to understanding systems. It helps us see patterns, it helps us see trends, it helps us see long-term behavior. But it also shows us something else: variability, uncertainty, and the limits of what we know. Because even with long-term data, we're still interpreting a complex system. We're taking just snapshots without it, and snapshots can be misleading. And with problems like PFAS, plastics, and other emerging contaminants, that long-term perspective becomes even more important, because these systems don't respond quickly. They respond slowly, over years, over decades. And that means our understanding and our response has to operate on that same time scale. Okay. So monitoring helps us understand these systems change over time, but it's reactive. It only tells us after it's happened. And another way to think about it is design. Designing chemicals and materials differently from the start. Because if you think about it, many of the challenges we're talking about, persistence, mobility, complexity, these aren't just environmental problems. They're actually design problems. And if we'd been asked these questions earlier with DDT and PCBs, we may have been seeing a different outcome. Because those decisions were made earlier when these chemicals were first developed. Decisions about stability, performance, durability, without fully understanding the long-term consequences. Because ultimately, we shouldn't detect problems, we should design them out. Not just how does it work, but how long will it last, where will it go, what will become over time, and most importantly, what happens after we're done using it. Because once these materials enter the environment, we no longer have control over them. And at that point, we're going to rely on monitoring and response instead of prevention. This isn't easy, this isn't always possible, but it represents a fundamental shift in how we think about these problems. Because the most effective way to deal with contamination is to prevent it happening in the first place. It is the pollution prevention way. We've talked about measurement, we've talked about monitoring, we've talked about design, but none of this matters unless it leads to action. In reality, that action just doesn't happen in one place. In some cases, it happens through regulation, like what we saw with DDT and PCBs, policies, standards, restrictions on use. In other cases, it happens through industry decision, voluntary phase-outs, reformulations, changes in how products are made. And increasingly, it's happening through consumers, through awareness, through demand, through choices about what we use and we don't use. And it all depends on something else: communication, education, and outreach. Because science only matters when it's shared, understood, and applied. And this is where programs like the Indiana-Illinois Sea Grant play a critical role, helping translate science into real-world decisions, connecting researchers, communities, and policymakers, and helping making conversations like this possible. So action doesn't happen in one place. It happens across systems, across institutions, and across people. And all these have to work together if we want to get ahead of the problem. Because if it's one thing that we've seen here across all these examples, is that we don't know when these problems began. We didn't know when these problems began, sorry. With DDT and PCBs, they weren't obvious problems at the time. They were solutions. Solutions that worked for problems that we were trying to solve. In many ways, that's still true today. With the chemicals and materials we're talking about, they exist because they serve a purpose. They do a great job. But because they solve these problems, because they solve real problems. But now we recognize that pattern. We saw it with DDT, we saw it with PCBs, we're seeing it again with these contaminants. So the question is no longer whether this pattern exists, but whether we take it into account moving forward. Whether we use what we've learned not just to respond to problems, but to prevent them, to design them out. And I lost my place. Okay, because today we're in a different position. We can detect earlier, we can understand more, and we can act sooner. But we're still learning and we're still making decisions with uncertainty. So we didn't know then, we're learning now, and the future of emerging contaminants will be shaped by what we do today. Thank you for listening. Questions? Oh boy. Whoa, okay. I'll take the gentleman first.
Very interesting talk, great insights you had there. Great. Again, thanks, John. There's some good insights there. I'm a geologist, so have done a lot of contamination work for years. So always the one thing you want to do is you want to behead the source. And in kind of more general terms, I guess, if and I know from other conferences that there are scientists within these companies who are doing work trying to get these things beheaded off top, but it's kind of I don't know what your insights are in the industry, but have you seen companies do like early detection and do all these things like risk assessments and
Absolutely.
all this kind of stuff, and leading to the marketing testing? It's great expense to the companies up front.
Yes.
But have you made some inroads into getting some of these companies to do this stuff up front?
They do. In fact, we saw one yesterday, right, Sarah?
Yeah.
Sarah works at Dow Chemical now, and she's looking at a lot of this stuff up front. And at ACS, I attended some of the talks by the people at Bayer, the pesticide company, and I was really amazed at how much work and time and money went into pesticide testing. I mean, they really do try hard. I mean, and they do a great job. And without it, we would be completely flying in the dark. But it's hard. It's nearly impossible to anticipate every outcome, right? It's very, very difficult. We probably would never be able to release any chemicals if we had to test every single scenario under every single situation. So there is a trade-off there. I mean, but I definitely think we need to be more diligent in things that are used at scale, especially large volume stuff, plastic eventually. I mean, look at how much plastic we use. It's just an incredible amount of material. So those are the things that we need to look at the hardest, is the things that get used at the largest scales. Nancy. Oh yeah, you need a microphone, yeah. Sorry.
And so, speaking of industry, a lot of times they're trying to develop these chemicals to be persistent
Sure.
to solve the problem.
Yeah.
So that's a fine line. How do you kind of work around that if you need it to be persistent, but yet then that means it stays in the environment?
That's why we have these problems, right? I mean, it's like plastic. It's designed to live forever, but intended only to be used for a couple minutes. And it's hard to find a material with those properties that will just break down at the very right moment. So that's definitely a challenge, is the persistence. I really don't have a good response for that beyond that. So, anybody else? Yes.
Thanks for your talk. I think a lot of it resonated with a lot of us. I do want to push back a little bit on this last quote that you have, because I think, at least for those of us that work in the PFAS world, some people did know.
Oh, that's true.
I mean, I think that there's things that were
Yeah.
known in health effects as early as the 1960s. And so
That's true.
One thing that I think I really like your conversation about designing better, but and I know I'm asking a physical scientist a little bit of a social science question, but what are your thoughts on the incentive structures for that? Because when you have a for-profit company designing something, and if the persistence is helpful to do, like you said, these are useful qualities that a chemical has, but that also have these unintended consequences. But if you're not responsible for those unintended consequences, where's the incentive to disclose those unintended consequences and be incentivized to design better? I know it's a big question. So
it's okay. I'll take a stab at it. I will start off with saying you're correct about the PFAS thing. And when I wrote that, I wasn't thinking about PFAS at the time. Rob Beloit, I don't know if you guys heard of him, Dark Waters. I was on a panel one time, and I told him I was doing emerging contaminants and PFAS. He got all mad at me. He said, I've known about these things since the 70s. And he was right. I mean, so I get it. You're right. But with industry, one of the things is pollution, in my mind, is a result of an inefficient process. And it's really lost revenue for them. So I think if you can convince industry that there's an economic reason to pollute less, that will solve that problem. They will find it. And we've done that at the Illinois Sustainable Technology Center for over 30 years as part of the pollution prevention way. I know I'm starting like a broken record, but that's been the core of it. So that's a major part of it, definitely, is make it an economic incentive for them to reduce this pollution. And also liability. I mean, when we look at what's happening with Dow Chemical and PFAS, maybe that's going to make them think twice, right? And 3M, I'm sorry, 3M I meant, not Dow, but you guys know what I'm talking about. Thank you. That's a great question.
Thank you. John, fantastic talk, man. Wonderful. I'm curious, though, a lot of the points you made at the end are really forward-thinking. AI and machine learning,
yes.
digital twins are starting to proliferate into our field as well. What do you think the strongest role that these technologies have to play without going too far into reliance on them?
Yeah, that's a great place to start, right? Is to, see if machine learning and AI can look at a chemical and predict how it's getting, especially with all the data that we have, if we can feed into it. That a lot of that even is with discovery of making new catalysts and making new pharmaceuticals. Now they can model a lot of that up front, so they're not creating so much pollution, all the effort in the lab work that takes to do all that discovery work. So there's definitely a role. And actually, I thought about putting a section in my talk about AI and machine learning. The problem is I don't know enough about it at this stage of the game. I only know enough to make me dangerous. So, but I think it's definitely got its place. And I'm very excited to see how that evolves. I think that's very important. Nowadays, any project that you work on really needs to have an AI component. So, great question, though. Great point. But technology will never always get us out of everything. We can't always tech our way out of everything. Okay. Yes?
So, from the people I've met, and tell me if I'm wrong, I may be the only person in the room that kind of represents industry here. I work for a chemical manufacturer.
That's unfortunate. To be honest with you, that's very unfortunate. But although we saw Sarah yesterday give a talk from Dow, but we need more of you guys here.
So, from a PFAS perspective, our real only exposure is AFFF.
Yes.
And it's built into a lot of our manufacturing and warehousing facilities. And the cost to replace AFFF is extravagant. I mean, not only do you have to replace the foam, you have to do studies to find which foam works. You have to replace your entire infrastructure around sprinkler systems.
Yeah.
You have to dispose of the old foam, which no one wants. So, and I sit in some of these rooms where we talk about budget and when we can do it and what the process will look like. And then at the same time, you have people sitting there on your fire brigade that are saying, this new stuff doesn't work.
Yeah.
If we have a big fire, I need to use this foam because it's the only way I can save people and infrastructure. So I'm just kind of wondering your perspective. And one thing you said is the science or regulation outpacing the technology. Wanted to get some more of your thoughts on that.
That's not an easy. You guys are not asking easy questions. I guess it's the kind of talk that I gave, though. I asked for it. Yeah, it's the trade-offs, right? I mean, DDT, for example, saved a lot of lives. It protected people. We were able to have better crop productivity. So I mean, it's the trade-off of, what do you want to do? Do you want to save more lives from fire? Asbestos too is another one that saved a lot of lives from being a flame retardant. So it is a really tough trade-off, and that's really above my. I just don't have an answer for it.
I will also say that a lot of the regulation around firefighting was built on specifications that you can meet with AFFF, like how it can take fire.
Yeah.
So you can't even meet those specifications. Some of the new technology.
Yeah. I'm really glad that you came, though. We definitely need more industry here. And actually, we need to also be present in industry. You don't kind of feel like you're in the lion's den, do you? But no, please don't. We want you to come and be part of this conversation. Such a very, very important part of the puzzle. So, definitely. Thank you.
Yeah, just want to follow up. Thank you so much for the great presentation. Just to follow up with your
Ooh.
question, but not another question, just a comment. Yeah, it's super expensive to replace those chemicals, but it's also, we are just like a shifting where we put our budget, because if we are thinking about how expensive is it for create a new chemical, it's also super expensive to treat the damage that those chemicals are causing to the environment and also to our health.
Yeah.
So it's super expensive to deal with this budget.
That's right.
So we have to think about that. And also, as you brought with DDTs, we had arsenic before, and then we shift to DDT, and then we shift to Mirex and to other things.
Sure.
There are solutions. And with PFAS in specific, AFFF something hard to replace, but if this is like can be an essential use, but you have others like a non-essential use that we can replace. Why do we need PFAS in mascara? Why do we need PFAS in food packaging? So there are things that we could now, and we are doing that with in states like California is banning PFAS in food packaging in other states. So there are efforts that we can do right now. We are able to do that. But we need the conversation with the industry and us, the scientists, to bring this up, just like a comment.
And it also reinforces by talking about the social sciences, right? I mean, I'd love to get somebody that can put the dollar value on these things. We need like resource economists. Anybody, any resource economics people here? No? Okay, well, definitely we need to get those people in conversation as well. I've always wanted to do that for plastic pollution because I think that, Kevin O'Brien once said to me that he thinks there's a lot of, because plastic's cheap, and that's why people use it so much, but there's a lot of hidden costs associated with plastic and when it gets to the environment, how long it lives, and we're not considering that, and I think if someone could put a dollar amount to that, that'll help us convince people that maybe to reduce the amount of plastic that we use. Important stuff. Okay. Anybody else? Okay. Go ahead.
Thank you. I really enjoyed the talk.
I'm glad that you're the one.
I just was curious because we talk about, and you talked about the design of better chemicals and things, and then you had mentioned like the firefighting foam and things like that. And so I work in a systems perspective, so I was just curious how much you hear about how designing the entire system impacts the design of the chemical, because I think of firefighting, and when we're talking there, we have ways to build buildings that are 100% fireproof right now, but the material is not really used, and it's natural and a carbon sink. So it just makes me wonder how much do you hear about the systems perspective of how we can get rid of a thing over here so that we don't have to have this chemical, or we can design it differently because we changed this piece of a system.
Yeah. A lot of I think in the past I'd heard these like making green chemistry a curriculum in the university, engineering and materials design and all that. And I don't know if they're still doing it or not. I'm sorry, I graduated 30 years ago or whatever. I'm not sure what the curriculums look like. I think that's important to still have that and maybe beef that up. Definitely education. Educating people who are making these decisions, that are making these chemicals, I think would be really helpful. Getting this problem solved up front. I think, did that answer your question, or did I just skirt around it? Correct.
Yeah, it's just, you don't hear much of that.
Yeah.
It tends to be more of a single focus.
Sure, but I mean, I'm not in industry, so they might actually be in a boardroom or somewhere in the design process talking about this, possibly. I just don't know about it. But
A simple answer to that is, if you have a warehouse where you want to stack chemical drugs 4 high, then there's specific targets you need to hit.
yeah,
If you want to stack them too high, you may be able to design a system that doesn't use foam, but you need a warehouse that's twice as big. So,
yeah,
I mean, that's kind of we're talking about
Yeah.
building in to the system components that don't require.
And using other cheaper methods that
yeah. It's important, though. I mean, obviously, immediate human health protection is going to take precedence over everything else, right? I mean, like COVID. I mean, people needed to wear masks so we don't spread COVID, but it was a major plastic pollution problem, right? But because we were instantly focused on protecting human health, that will always take precedence. All right, anything else? Anybody else? All right, well, thank you. Thank you very much.